Okay, we're going to look at adding, subtracting trig formulas. So we have a trig equation here, cos theta times cos 5 theta plus 0.5, that's not that definitive, let's put that there, is equal to sine theta times sine 5 theta. Okay, so this is confusing. The question is asking us to solve for theta, so we got to find theta such that theta is an element of all the real numbers, which means there's lots and lots of versions to this. So we're actually going to probably find an equation for theta because this is going to be probably a sinusoidal type of function. Did they give us a range? No, they didn't give us a range, so there's going to be quite a bit to it. To start off, a lot of these equations, what we're trying to do is get everything on one side, set it equal to 0, or to some kind of function that we have like a special triangle for. So I'm going to start with moving the entire right side. So we have the right side of the equation and we have our left side of the equation. I'm going to subtract sine theta, sine 5 theta, or sometimes called, switching it over and using the opposite operation. So we'll go cos theta times cos 5 theta. Okay, and I'm purposely going to move it right beside it. Sine theta cos, that's not right. There it is, sine 5 theta. So essentially what I've done is I've moved all of this over as one term. Sometimes that can be a little confusing. Let me finish out the next line here. Plus 0.5 is equal to 0. If this move is a little confusing, you could always, and I'll move over to the side to demonstrate it, you could always put a little let statement in. I could say something like let x, since we don't have an x in this one, equals sine theta sine 5 theta. And that way when I go to write it out, we had our cos theta cos 5 theta plus 0.5 is equal to x. And then when we move x over, we still have cos theta cos 5 theta. Should have done this all before on that other step. Is equal to negative x, okay? Is equal to 0. So that might be algebraically a lot easier to look at. We replaced that whole right side with just the letter x, and then we moved it over. So when it was positive, when it came over to the left, it became negative. And then, well, x isn't really part of the equation. We actually have to sine theta. We substitute it back in for x. So when we substitute it back in, we end up with this cos theta cos 5 theta plus 0.5 minus sine theta. I don't have enough room. There we go. Sine 5 theta is equal to 0. Okay, and then all I did was rearrange it the order. There are 3 terms at this point. We have our first term, second term, and our third term. Our operators, like plus and subtraction, they separate terms for us. We have 3 terms in this. So I very quickly jumped all the way over here, but these are all like those intermediate steps. There's quite a bit that we actually did there. Once we get to this becomes a question of finding some identities. Is there an identity I could use that might help me simplify this part of the equation? Okay, so I'm going to flip over your paper. I thought a little earlier. We have one identity. Cos and sine. Perfect. So there is an identity. We'll write it in green here. That looks like this. It says cos x plus y is equal to cos x cos y minus sine x sine y. Okay, when I look at this right-hand side, I actually see what I have up here. The only difference is that x in our above case, x is actually equal to theta, and y is equal to 5 theta. Otherwise, this is sine and sine is what we have here, sine and sine. And we have cos and cos, cos and cos, and a subtraction sign in between. So I have that identity. And what that's telling me is I can condense everything into this version. But instead of writing x and y, when I condense it, I'm going to replace x with theta and y with 5 theta. So it would look like this, cos theta plus 5 theta. Okay, so now that we know this piece here, I can replace all of that, which is this huge piece here, with what we've circled below. So it'll now read cos theta plus 5 theta, and then we write the rest, plus 0.5 is equal to 0. So now we kind of scroll down our algebra. This is way simpler to look at. This is much nicer. And in fact, these are like terms. Think of this having like a coefficient of 1. So that's 1 theta plus 5 theta. Well, I can just add the coefficients together. So I get cos, that's not an S, cos 6 theta plus 0.5 equals 0. Okay, that's nice. I'm trying to look for a scenario where I'm going to use some special triangles. So actually working in decimals is not so wonderful. I know off the top of my head, and if you draw out your special triangles, you'll realize that we do a lot of the recognizing of sides and stuff by fractions. We have a scenario where you have one of the triangles that looks like this. It is 1 root 2, and another one is 1 2 root 3 as the sides, okay? And when we refer to sides, we usually have a fraction of one side over another. I'm going to change this into a fraction. Off the top of my head, I know that 0.5 is a half. So I'm going to say cos 6 theta plus 1/2 is equal to 0. And then the goal is, I got to remember the goal in this question. They originally told us we got to figure out what theta is. So in other words, I got to get theta by itself. So I want to move that half to the other side of the equation. When I do that, it becomes a negative. So we still have cos 6 theta is equal to -1/2. Okay. And what we want to do here is we're looking for a scenario. We need to figure out what this is equal to. So first of all, we can look at our special triangles. We have a special triangle here. And this is 1 over, if I'm looking for cos, depending on what angle I'm at. So if I'm not sure which one to test, I'll go through them all. If I'm at this angle here, we can call this one theta to start. Cos is my adjacent side over my hypotenuse. So this ratio would be, depending on this angle, these angles are all actually pi over 4. You guys work in radians or degrees? Which
like
is also
both?
45 degrees. Well, I'll put both in
usually
there.
radians, I do.
They probably
Yeah.
want radians, yeah. So when I look at that, that gives me a ratio of 1 over root 2. That's close, but not quite. This is not a root. So, and because these two angles are the same, it's not going to be that triangle there. If I take a look at this angle here, I call this theta, and I'm looking for the cos of it. This is my adjacent, this is my hypotenuse. That is root 3 over 2. Not that angle. What if it was this angle? If I go adjacent over hypotenuse, I end up 1/2. Okay, that's important. I just got to remember what angle this is. I've memorized them. It's probably helpful if you do too. This will be 60 degrees or pi over 3 in this case. Oh, good memory. Excellent. Okay, so we got that information. But I also got this pesky like 6 times theta. I'm going to use that let statement again to simplify this. I'm going to say let z equal 6 theta. I'm just using a different letter because we used x up there before. So now this becomes something a little simpler to look at. Cos z is equal to -1/2. Okay, well, we've just discovered that we're looking at this angle here, pi over 3. But what's also important is it's negative. So I got to draw that Cartesian plane, just like we had talked about before. We're going to draw it, and we got to put our cast system in. So we have CAST, always, someone told me one, are always Scarborough Town Center, something like that. And this one just tells us what's positive and what's negative. So everything's positive here, and since our answer is negative, we're not in this quadrant. Only sine is positive here, so cos would be negative in this quadrant. Only tan's positive here, cos would be negative here, and only cos is positive, so it wouldn't be there. Okay, so what we have now is we have this scenario. I'm going to do it over both. We're looking for 2 angles, and they live in that space. We know that the internal angle is pi over 3 on both of these, pi over 3. What we need to find out is what is this entire angle all the way here, okay? So you take a look at this. I know if I'm working in radians or degrees, if I go halfway all the way to here, that's pi. So essentially what's happening is I'm going to use this trick. I'm going to go all the way there, which is going pi, and then I actually got to go back. And I go back exactly this much, pi over 3. So this is the idea of subtracting an amount. So if we say pi, subtract pi over 3, you can use your calculator. It'll quickly get you an answer. I can tell you right now this is pi 3 over 3 minus pi over 3, which gives us 2 pi over 3. That's my first angle. I can also use that exact same fact. I'm going to go all the way to pi. And then this angle here, well, that's just going past it, pi over 3. Same concept. 3 pi over 3, that's the same as pi, plus pi over 3 is 4 pi over 3. There we go. We got two angles, one of them and the other one. So I'm going to take our algebra. We set this up here. It turns out that z, move it over here, z is equal to 2 pi over 3 and z is equal to 4 pi over 3, which would be great. Looks like we're done, except that this question never asked about z. So we have to substitute back in. What did we replace z with? So we replaced z with 6 theta. So we're going to replace that now. We're going to go back, and this says 6 theta is equal to 2 pi over 3, and 6 theta is equal to 4 pi over 3. Well, now to isolate theta, we divide both sides by 6, just like dividing this by 6, divide this by 6. And if you do your calculator very quickly, you'll get theta is equal to 2 pi over 18, which I can simplify, and theta is equal to 4 pi over 18, which again, we can simplify both of these. So we now have something that has changed. This value is much smaller than the one we were working with before. This one's actually pi over 9. This one is 2 pi. 2 pi over 9. Okay? Pi over 9, 2 pi over 9. If we were to go back to our Cartesian plane, we could see that occurs more often. We're going to jump out and take a look at everything we've done here, because it was a heck of a lot of work. It's a huge question. Tons of info we've done here. But like we said before, at the very beginning, I mentioned that they didn't give us a range. They just said, tell us all the thetas. Well, this is a sinusoidal type function. It's going up and down, up and down, up and down. So I'm going to show you a graphical representation to help us make sense of the very end of this. Let's see. Let's do this. Desmos. We had found out that cos... Oh, what is this here? That's something already saved. We had cos 6, let's say x here. Notice that this is occurring very quickly. So these are technically in radians. I'll show you 1 radian here by using an x value. X is equal to, let's say pi. So there's 1. And then we'll give another one at x equals. The reason I'm using these two is this one is halfway around the circle, the other is all the way around the circle. If we notice, this period is gone much faster. And that's because of that 6 pi that we had. Our period has picked up. It's much more frequent. So our answer is technically we're looking for when it intersects the value of -1/2. So if I put a y through here, remember we originally only had 2 answers. But if I say y is equal to negative 1/2, and we start, let's say we're starting at 0, we go 9 pi and 2 9 pi. Those are our first 2 answers, except that this one's an answer, this one's an answer, this one's an answer, this one. Oh my God, look how many answers we're getting. We're getting tons of them. So we got the first 2 answers, which is really important. They given us between 1 period. So this is the period. It takes 3 pi as a period. So we've got 2 of them, but we have to figure out how often this thing repeats. So we're going to jump back to our other work and just do it algebraically. I can visually see, but I may not have a graphing calculator on my work. So I'm going to go algebraically how to solve this piece. So I'm going to zoom back in here. Okay. What we have to figure out is we got those 2 answers. And they're going to be repeating answers. And what we found was we had technically cos 6 theta, okay? This here is a transformation. It's a horizontal compression. If you remember the general equation, it looks something like this. A cos, you might have used different letters, b x minus c plus d. Maybe that's familiar to you. You might just use different letters. Sometimes k, sometimes they use k for this one. Is that more common? Yeah. This has to do with horizontal stretches and compressions. This also has to do with the period. So if we think of a regular cos function, let's say it was just cos theta. Whoops. It takes, when we're going around a circle, the period is 2 pi in that case. Okay? But what has happened is we have this value of 6. We are compressing this. So in other words, this is getting pushed inwards. It's happening more and more frequently. And a way to figure out the period is we would multiply by 1 over b, or in your case, 1 over k. Okay? If this is our k value, which is 6, our new period would be 2 pi times 1 over 6. That becomes 2 pi over 6, which simplifies into pi over 3. And then if we go and take a look at our answer, we'll notice that this thing repeats pi over 3 over and over and over again. So we should actually be giving an equation to these two answers. I'm going to show you. The equation is written like this. It can get a little confusing, and maybe your teacher doesn't want this far. We'll find out. We have theta is equal to pi over 9 plus, usually they'll say something like n times pi over 3. And the other version is 2 pi over 9 plus n times pi over 3. We say n times pi over 3, and normally what they say where n is an element of all integer numbers. And all that means, if I make this 1, if n was 1, I multiply by 1, I get my next one. If n is 2, I multiply this by 2, I get the next point. This is a repeating pattern at this point, okay? I don't know if your teacher is going to take you that far in the answer. We technically found the two values, but because this is sinusoidal, something that's repeating, normally you would give an answer as an equation at that point.